All right, we're going to be talking about free body diagrams. So, a free body diagram is essentially just a drawing or a diagram that we're going to be making a lot in class that looks at all the forces that are acting on a single object. So, just one object. A free body diagram has all the forces labeled with their magnitude and direction. So, remember, magnitude is the number value. So, maybe it's 10 newtons. And then the direction is indicated by the arrows. So this is one example of what a free body diagram would look like. So you have a applied force going to the right, a normal force going upward, friction going to the left, and gravity going downward. So let's talk about each type of force that we're going to be drawing on free body diagrams. So the first one, let's talk about air resistance. So as you can see in this diagram, you have a person jumping out of a helicopter, and as he falls, you can see that the force of air resistance continues to grow. So it goes from 350 to 700 to 833, where eventually it does match the force of gravity. They're both 833. So air resistance continues to become greater as you fall. You can actually increase air resistance by adding parachutes. So air or air resistance is one of our types of forces. The symbol that we're going to be using when we draw it and label it on a free body diagram is Fa. So it's a frictional force of air that air exerts against a moving object. So a type of friction, but it's with air, not with surfaces. It is opposite to the direction of the motion of the object. So if the person is falling downward, notice how the air resistance is going upward. All right, next we're going to look at an applied force. So an applied force could be a push from a person. So it's a push or a pull. So force applied is recognized by the symbol Fp. We can't use Fa because that's already taken with air resistance. So we do applied, has two P's, so Fp. It's a general term for a force applied to an object by a person or by another object. And the direction of this arrow is the same direction as the acceleration of the object, bearing any resistant forces. So if the object's moving to the right, the applied force is going to the right. If an object's accelerating to the right, the applied force is going to the right. So the direction of the acceleration of the object matches the direction of this applied force arrow. All right, next let's look at friction. So we know the friction slows the motion, right? So on these free body diagrams, FF is the symbol that we're going to be using. Friction is a contact force that acts to oppose or work against sliding motion between surfaces. So if this box is moving to the right, friction goes in the opposite direction, so to the left. Friction is always parallel to the surface, so notice how the surface is this nice flat surface, and the friction force is parallel as well to the surface. But it's always opposite to the direction of the sliding or the movement. So if the object's moving to the right, the friction is going to the left. It's always opposite. All right, next force we're going to look at is a normal force. It's an upward push by the floor or whatever surface that the object is resting on. So normal force is written as Fn, that's the symbol. It's a contact force exerted by a surface on an object. It is always perpendicular and away from the surface. So we're going to be mostly looking at horizontal surfaces, so these nice flat surfaces. All right, the normal force is always perpendicular, meaning it can form a right angle. So your normal force is always going to be upward at a 90-degree angle to the flat horizontal surface of the floor. All right, next one we're going to look at is tension. So tension is Ft, T for tension. It's a pull exerted by either a string, a rope, a cable. Usually it's an example of something hanging. So maybe by a string or a rope. And the strings are always pulled taut. That's important too. If their strings are not pulled taut, then there's no tension actually involved. So we could be talking about a pulley system. It could just be an object hanging by a string or by a rope. But the direction of this tension is away from the object and parallel to the string or rope. So for this one, for this first one on the left, we have two tension forces. So something is hanging downward, like with a pulley system being used. We won't be seeing a ton of these examples in physics. Mostly we're going to be looking at examples such as the one on the right. So maybe you're walking and you're wearing your book bag on both your shoulders. An example diagram could look like that. So although the book bag is hanging downward, the tension of the straps are going upward. So that's why you have these two tensional vectors going upward. All right, and weight. So remember, weight is a force measured in Newton. So the symbol for weight is going to be Fw. It's a field force due to gravitational attraction between two objects. Generally, we're going to be talking about the attraction between Earth and an object. That's what gives us weight. Weight is always straight down. Always. Weight always goes towards the center of the earth because the gravitational attraction of earth on us or on some object is trying to pull it towards the center of the earth. So weight is always going to be downward, straight down. All right, let's do a couple of examples. So problem 1. The book is not moving. So you have a really pretty purple book resting on a table. So are the forces balanced or unbalanced if the book is not moving? Yes, they are balanced. So remember, balanced means that it's either not moving or maybe it's a constant motion. So we've talked about like cruise control, constant motion. The book is sliding across the table at a constant 2 meters per second. Well, in this case, it's not moving at all, and there's no applied force. No one's pushing the book. It's just sitting there. So to draw the free body diagram, we know that this book has some sort of weight because gravity is acting on it. So we would have the force of weight going downward. And then because the object is resting on a surface, you also have a normal force, so Fn. So when we draw this, you can do it with a box or a dot. I like to do it with boxes. And you're going to have the normal force going upward and the weight force going downward. All right, number 2, a rightward force is applied. So in this scenario, we have an applied force. So remember, that's going to be Fp. To a book in order to move it across a desk at a constant velocity. Constant velocity. So that means it's just going the same speed the entire time it's crossing the table. 2 meters per second the whole time. It's not accelerating. And we're going to construct a free body diagram for the book. All right, so again, it's on Earth. Gravity is acting on it. It has weight. So we have the force of weight going in the downward direction. We have the normal force opposite to that. We have an applied force that is going to the right. So remember, that's Fp because Fa was air resistance. And then we have two surfaces that are interacting with each other. The book is pressing down on the table. The table is not a perfectly lubricated, smooth surface, so there is going to be some friction involved. So if the book is moving to the right, like because the rightward force is applied to the right, that means that your friction, Ff, is going to be going to the left. So your free body diagram should look like this. And notice it is a constant velocity that we're looking at. So all of your arrows here should be the same size. So notice how your force applied is equal to your frictional force. They're the same length.